everyone, it is my pleasure to share our recent research on design of linear and planar arrays with low side lobe levels and high directivity using two-way array factor. In the radar system, the same antenna element is used for both transmitting and receiving the radio signals. In such scenarios, the analysis of the two-way array factor is important since it accounts for both transmitting and receiving the radio signals. The major problems are presence of minor lobes near the main beam, which will create the interference and ground clutter of the radar system. The other problems are low directivity and poor tapering efficiency. The two common approaches to reduce the side lobe levels are by using the amplitude tapering, and the second one is thinning. Amplitude tapering means feeding the antenna elements with different excitation values, which will basically increase the complexity of the feeding network, and it also reduces the tapering efficiency. Thinning means deactivating the antenna elements, which means the number of active elements are less. In this case, the directivity is degraded. Therefore, in our approach, we use the two-way amplitude distribution in order to lower the feeding network complexity, and no thinning is involved, which means the number of active elements are high. Therefore, the directivity is improved. We propose a linear and planar arrays where the antenna elements are illuminated with two different excitation levels. The sum of the elements in the center of the array that are excited with higher weights are determined by the following equations, while the remaining adjacent elements are illuminated with lower amplitude weights. Therefore, the number of elements that are excited with lower and higher amplitude weights and their respective values are determined by using an exhaustive optimization procedure. This graph shows the exhaustive optimization procedure for our design parameters. It concludes that the minimum side lobe level of -52.18 dB with a minimum loss in the directivity is observed for both linear and planar arrays. Now the question is, are these solutions are valid for other array sizes? To verify this, we have varied the linear and planar arrays extensively. In all the cases, the side lobe level remains below -52 dB and the loss of the directivity is constant. We also propose a feeding architecture where the number of components are drastically reduced compared to the conventional approach. To validate the feasibility and robustness of our design in the realistic scenario, we have considered a microstrip patch antenna and simulated using the CST software. It shows the good agreement between the simulated and theoretical results. This slide shows the comparison between the proposed work and alternative designs. It concludes that the proposed design shows better side lobe level reduction, lower directivity loss, lower feeding network complexity. Also, the proposed design shows the best trade-off between the side lobe level reduction and tapering efficiency. Similar observations are made in the planar arrays. Thank you for watching.